Our first guest is Alvi, the Turing Group Program Manager at Microsoft. Microsoft's Megatron Turing model is one of the largest AI models ever built, with 530 billion parameters. And these are the values that a neural network tweaks as it trains. Ali, welcome to EmTech Digital. Thank you. Take it away.
Thank you. Good morning. It's great to be here. Day 2, kicking things off. It's 6 in the morning, West Coast time. I've been up since 4. So if anyone in the audience even yawns, I'm just going to pass out and fall asleep here. So let's try not do that, right? My name is Ali. Like Will said, I'm part of the Turing team at Microsoft, and we build large-scale AI models, and we productize them in Microsoft products. Today, I'm going to talk to you about how large AI models are transforming how we build AI algorithms. And for that, I'm going to take you back in time, way back in time, to about 4 years ago, if the clicker works. Oh, there you go. This is a classic example of a problem that we face in search where you have a question in a passage, and the idea is to find out whether this passage answers that question and find out where in that passage you have the answer. In the traditional way of doing this, you would probably have to do all of these things. On the query side, you will have to create lots of features. You'll have to do dependency parsing, parts of speech tagging. On the passage side, you would look at the document that the passage came from, and you'll do the same kind of NER tagging, look at all of other features on this document, and then pass all of that information into a massive ranker, which probably contains a lot of these classical features from semantic matching using translation models, NER tagging, some BM25 similarity models. And at the end of all of this, you will probably get whether this is actually a good answer for this question and whether to show this or not. Now, there are a lot of problems with this approach. In order to build this, you have to build many, many small different components or AI models. Each one of these requires its own data sets. You have to label a lot of data to get these models to be built. These models cannot be used anywhere else because they were only specifically for this task. We are optimizing for every single problem in its own. So at the end of all of this, you'll have a whole bunch of these AI models. And depending on if one of the AI scientists did not optimize well, the entire system is now going to be inefficient, and you won't be able to optimize the entire system as a whole. And of course, I'm talking about English here. So if you wanted to do this in French, if you wanted to do this in Spanish, any other language, you would, again, go back to the drawing board and start from scratch. So now, let's fast forward to today. The modern way of doing this Q&A is you have an end-to-end deep learning model, and this takes raw query input. It'll take the raw passage input, and at the end of it, it'll tell you whether these passages are relevant. It'll tell you whether you should trigger this whole experience. It'll tell you specific parts of the passages which answer the question, and it'll also do some inference and tell you what the direct answer for this question should be. And the same deep learned model now can answer this question or similar tasks in Chinese, Japanese, French. We have this model in production. It does it in 100 different languages, and it's the same exact deep learned model. So how do we build these end-to-end deep learned models? So it starts off with what we're going to talk about, like a foundation model with some label data, and you perform fine-tuning for all of these tasks, relevance, triggering. We saw all the tasks that it has to do. At the end of that, you get a model which is called a teacher model, which is very, very good at doing all of those tasks. Now, once you have a teacher model, you go through a process known as distillation, and you get all the other information that teacher model has out of it only to focus on the tasks that you have at hand, and then you get a student model. Then, depending on your production requirements, you might have to go through optimization, quantization, compression, all of those things to get what is finally the model that you deploy in production. Now, the key thing is, when you look at the traditional way of doing NLP, you needed experts. Nobody else who did not understand NLP could solve those problems. Everything in this pipeline does not require any knowledge of NLP. You can basically have any applied scientist who can come in and do this within a day, and it'll be able to beat any traditional model that did NLP for this task within a matter of a day. And the cool thing is, all of this is transferable. So if you're doing this for NLP, you will be able to do this for any task in NLP. You can even do this for computer vision. You can do this for all other categories of tasks that person is trained for. So you don't need specialists anymore. You can have a generalist to do this. What is the key thing that makes all of this possible? And that's what a foundation model is. So let's take a look at how we got here. This is a chart from Andrew's book, Machine Learning Yearning. This chart actually is very interesting because it talks about the amount of data and its relationship as it pertains to the performance of a neural network. So a couple of observations that you have here is, of course, more amount of data means you'll have more performance. Data can even make up for lack of quality in some cases. As long as you have more data, you'll have better performance. Another thing is, the bigger the neural network or bigger the AI model, you'll have better performance. At the same amount of data, a bigger model can learn more from that data than a smaller model. But the last thing is the key thing. You see that there's a plateauing effect at the smaller scale of AI models. But as the model size increases, you can extract more performance by just giving it more and more data. So this is the trend that essentially resulted in this arms race of large-scale AI models. So this chart talks about the explosive growth in model size over the last 4 or 5 years. If you look at the large-scale era, which is about 2017 and onwards, this chart actually has parameters in a machine learning model on the y-axis and the timeline on the x-axis. The y-axis is actually log linear, so every point in the y-axis is an increase of 10x. So every model is an order of magnitude bigger than the model before. If you look at it 27 to 2022, we've had about 3 to 4 orders of magnitude increase in the size of AI model. That means it's 10,000 to about 100,000 times increase in the size of these models. How did that happen? Once we found out we can give more data to these models, we figured out there's this thing called self-supervised learning. So we no longer had to label data, which means we could feed these models everything in the world. Big companies came out and started building these supercomputers, which are fully interconnected with NVLink and InfiniBand, which started to provide us the compute to actually be able to train these models. Then there were systems and software innovations for model parallelism and data parallelism, which allowed us to scale these large models and use this compute to train these models. And then also there were some novel innovations around optimization, as well as new recipes that came along that made us very, very efficient in training these models. Here's another chart of a different way of looking at it. On the y-axis here, we have training compute in terms of flops, and the numbers go all the way up to 1 million exaflop, which is like 1 followed by 24 zeros. You can see in the large-scale era also, these models are using a lot of compute. The key thing, though, to notice is, even though the model size has increased 4 or 5 orders of magnitude in the last 4 or 5 years, the amount of compute needed to train these models has probably gone up about 1 or 2 orders of magnitude. And that's where we mean that the software innovations that have come along have made it possible to train these bigger models with the same amount or little more amount of compute. And that, just to give you an example, the model right at the top is the Turing Megatron NLG 530 billion model that our team trained. And this has an unprecedented scale in terms of the accomplishments that we did. So we had 8-way parallelism for model, 35-way parallelism for pipeline parallelism. So the model was split across more than 250 different GPUs. We had about 4,000 or 5,000 GPUs in all to train this model. And with that interconnectivity, we were still able to extract 126 teraflops throughput per GPU. Maybe a year or two ago, we were talking about theoretical maximum of 100 teraflop as a max we can extract. We were still able to converge the model, train the model, and still have 126 teraflops here. Of course, we gave over 300 billion tokens of data to this model to be able to be trained. So what is the result of all of this? So here's a chart that talks about some of the popular benchmarks that are used to measure performance of these models. The blue line, so the black line here is the human parity. So you can see key observations here would be, things that took about 20 years in the past to surpass human parity. Now we've shrunk that time to less than 1 year in some cases. So most of these benchmarks pop up, and within a year, we exceed human parity, which means that we are at a saturation point, or we are beyond the saturation point on most of these benchmarks. So you cannot anymore use these benchmarks to measure the performance of these models. Any improvement that you see are probably because of overfitting, or somebody has done a clever trick or got lucky, and it's getting a little more extra benefit out of it. So the key thing is, the real measure of quality is in end products. So we need to find an approximation of complex real-world tasks to be able to measure these models. So that's why anytime you use these models, do not rely on any of these benchmarks. You need to have good test sets to measure the product quality in the scenario that you're using. Here's a different way of thinking about this. If I go through the same journey in terms of machine learning followed by deep learning and foundational models, in the era of machine learning, we were learning how to do certain things. And it results in this, what we call a homogenization of learning algorithms. So you knew if you wanted to do clustering, there's a clustering algorithm. Or if you wanted to do, there's gradient boosted decision trees for certain models. Or there is SVMs. In practice, what that means was every single task had to be feature engineered using classical machine learning. So you had to have human creativity. I talked about the NLP experts that build these NLP tasks. You had to have insight and gut feeling. You had to have experience to know exactly how to solve these problems. And gut instincts, experience are not a very good approximation of real-world scenarios. So that was a big limitation. When we moved forward to deep learning, we started seeing emergence of features. So you knew, that there are deep models that can now figure out semantics inside of natural language. Or there are ways we don't have to come up with features for vision models. So it'll figure out the curves and the corners and the lines and the shape of the eyes by itself. And that resulted in what we call a homogenization of architectures. So you started seeing LSTMs and GRUs come along for natural language. You started seeing CNNs as a good model to do computer vision problems. In terms of practical application of that, we started replacing classical machine learning tasks with these deep learned models. So we said, okay, we have this complex system of question answering. Instead of doing a ranker and having a gradient boosted decision tree, we're probably going to have a small neural network that's going to solve the problem there. So the problem with that was it was still one-on-one replacement of classical tasks with deep learned model. You would get predictable bumps, but you still have to custom train models for each and every one of these tasks. Now, when you think about foundational models, we started seeing emergence of functionalities. So now we said, okay, we don't have to do any of these, rely on these features of the neural networks. The neural network can itself do question answering as a whole. So an end-to-end system will come along. And that resulted in homogenization of models. So instead of saying, okay, now we're going to use CNNs or we're going to use LSTMs, they said, oh, no, we're just going to use GPT-3 for generative tasks. We're going to use, Turing universal language representation model for all of our natural language tasks. We're going to use some, Microsoft research model for computer vision or an OpenAI model for all of our vision tasks. So now what people are doing is we're saying we're adopting pre-trained models and we're reusing pre-trained models to actually solve our tasks. The tasks are still the same, but we're not building any custom models anymore. And the big benefit of this is you benefit from the scale and the size of these large models, and you see big bumps in your performance. So what's in the future? The future is all about what we call interactive AI and unified models. And what do I mean by interactive AI is models that you can actually communicate with or interact with on an ongoing basis. And this will result in creating some new experiences, and I'll talk about these experiences. We will also go beyond some static interfaces. So the model is not going to be doing just one task, and it's not going to be transactional in nature. You will talk to the model will give you something, you will talk back to the model, and the model will be able to refine the results or give you more information. Also, a big thing that will come on, we've so far seen these big models in their own modalities. So you have text models, you have computer vision models, but you're going to see more and more that these models are going to merge together and have multimodal properties. We saw some talks yesterday about this. We feel like this is a big thing that's going to happen in the future. So here's an example, and this is going to be some examples from the Turing NLG 30 billion model that we trained. I want to give some context. You guys can read the riddle, and even if you have an answer, that'll be good if you can tell me the answer. This model has not been fine-tuned. This is as is, trained with no intention of doing any riddles or any other task. We have not fine-tuned it for anything. We were just playing around in a COVID era. We were having a happy hour, virtual happy hour, and people were asking each other some riddles. One of the guys came up with this riddle, and since we had this model, we said, okay, let's try and see what it does. So any takers on what the answer might be here? Yeah, that's good. So the model obviously comes up with the answer here, and not just the answer. The model actually continues to predict why it thinks the name is the answer. Again, this model has never been fine-tuned to answer any of this question. We've never seen this riddle before, and it actually, even though it gets a little morbid towards the end, but it came up with the name. Funny thing is, the guy who actually trained or came up with this riddle was thinking of the phone number as one of the answers that you could be for this riddle. If we run the model again, and you guys bought all of this explanation, sometimes it'll come up with phone number as the answer also. Here's another thing. We're at MIT. We had the IBM Watson lab here. Watson in the 90s was a moonshot project to try and see if they can solve Jeopardy or beat humans at Jeopardy. This model has never been trained to do any Jeopardy scenarios. We have not fine-tuned it. As a pre-training, this was not the target. After the model was trained, and Jeopardy doesn't repeat. The show is known to not repeat its questions. Sometimes once or twice that has happened. So we said after the model was trained, we put it to test against Jeopardy in the earrings after the model was trained. So here's one question saying, including Okaloosa and Escambia, there are 16 counties in the Florida region with this shapely name. And the model goes ahead and, of course, says, what is the panhandle? Another example here is, ooh, I want to take ya, but the Beach Boys completely made up this triple rhyme title island from a 1988 song. And the model just spit out, what is Kokomo? And these are correct answers. The humans actually perform at about 80% accuracy on Jeopardy. Our testing of the model shows without any fine-tuning or anything like this, the model actually does about 91% on Jeopardy. So this model is not connected to the internet. It does not have any access to any information retrieval system. This is just a standalone model running on a single machine, never trained to do Jeopardy. So these are the kind of emerging experiences that we see coming up. I talked about multimodality. We've seen that when we train models in a universal fashion, where we merge all of the languages together in a single model, the model starts to learn better about all the different languages by having exposure to all the different languages. But if you look at the screen, I can say the same thing, a beautiful sunset on the beach, in any different language, but it does not change the visual representation of the meaning of that statement. So that means there's a lot of information in a visual image about the language that I'm using. So if we can actually somehow take this information and feed it into a model, the model will probably learn better about the meaning of what a sunset is, what a beach is, what a beautiful sunset on the beach would look like, and how to kind of understand that the sequence of words so much better if it actually has a visual understanding. So we've trained models that actually converge these modalities together. In the future, we feel like you're going to see a lot more of this happening. These foundational models will have all kinds of data from different modalities being fed into them. And as a result, these models will be able to do tasks across a whole number of modalities. A couple of examples. We trained a model called Turing-Bletchley. And this model is a pre-trained model that actually fuses vision and language together. So now this is a very typical task of image search. And this model has not been fine-tuned for this. This is, again, running on a standalone box. It has never seen these images. These images do not contain any metadata. So all the model has seen is the visual representation of the images that you're about to see. It has no idea what these images contain, except for the pixel information that is available. So if you go and search for Tokyo Tower, and this database is about 50 million images, and it's starting to pull things from it. So you see the pictures of Tokyo Tower. Now you can add and say, OK, Tokyo Tower at night, and it starts to show you Tokyo Tower at nighttime. Then you can say, OK, multicolored Tokyo Tower at night, and it'll start to filter out the results that are not multicolored, and it'll show you the multicolored Tokyo Tower at night. Again, these images do not contain the words multicolored or Tokyo or tower or anything like that. These are just the pixel information here. It can also, you can do the same thing in any other different language. So here's a Korean example of saying optical illusion, colored picture collection. It comes up with these things. Now you can also, instead of talking to it in words, you can actually give it an image. So the first image here is a reference image saying, find me images like this. And again, none of these other images have any information. These images are basically different ways of saying thank you. And it figures out, these are probably the most relevant images that you can show here. Here's a car, VW van, which is making a comeback in an electric form. But it doesn't matter what the angle of the car is, it understands that this is the same entity. So the visual representation of these images is very, very different from each other, but the model is able to pick up and say, OK, all of these are the same thing. Here's an interesting thing now. So we saw language and we saw image. Now we can start to mix things together. So here's a picture of the ex, or also the future Tampa Bay Buccaneer quarterback. And if we say, OK, let's add the word Patriots to it. So now Tom Brady has actually played for the Patriots. So the model says, OK, then you're most likely talking about Tom Brady in a Patriots uniform. But then I can say, OK, add the word Packers to it. And now Tom Brady has never played for the Packers. But the model now understands that this is actually a quarterback. So what should I show? And it goes ahead and figures out that this is actually referring to Aaron Rodgers. Again, the model has no information about any of these images. We can do this. Here's a sketch of the Space Needle in Seattle, and we can add the word Paris to it, and it starts showing us sketches of the Eiffel Tower. We can say, OK, get rid of the sketch, and it shows us just the Eiffel Tower. Here's a PowerPoint of symptoms of coronavirus, and I said, OK, get rid of the word symptom, and let's do prevention. This model has no pre-training for doing any kind of OCRs. But it picks out the PowerPoint slides and shows you prevention of coronavirus. And here's one last thing where you say, keep calm and carry on. I said, get rid of the carry, add the wine in it. And it says, keep calm and wine on. Why not? It's 9 o'clock on a Wednesday morning. Some of the images actually don't even talk about wine. It says, keep calm and pour on. So it understands the concept of that thing, meaning, it is wine. In conclusion, the trend lines for large-scale models show no signs of stopping. We expect these models to be generative, multimodal, universal in the future. The training sets are going to be a limitation because we have run out of data to feed these models. But on the supervised setting, I talked about the test sets being saturated. We need more test sets here. Data cleanup is a big challenge. We need to do a lot of effort there. The new emergent experiences coming out of these models provide significant opportunity for disruptive experiences. Fine-tuning and in-context or a few shot learning will be the primary methods of using these big models. Compute will become cheaper. It'll be faster, so it'll provide us with the ability to continue to train these models, and the cost will be justified based on the amortization. Since the same model can be used across many, many tasks, you will be able to train these. The biggest challenge will remain to be productizing. Inferencing cost is a big challenge. These models are very large, so you need to optimize them. So based on that, that still remains to be an area of challenge for us. At the end, I would leave you with this quote from Andrej Karpathy, who last week wrote this article that talks about the neural networks and how they might look like in the future. Thank you.
Thank you so much. That was such a great intro to the day, setting up where we are and where we're going. My first question probably has a very big answer, but give a small one. We measure the size of these models in parameters. We talk about 530 billion parameters. And just to give a sense of where we have come from, GPT-3 a few years ago, which sort of gave the popular sort of indication of what these models could do, had 175. So we're growing still. What is a parameter, and why does having a lot of them give such great performance?
So neural networks are essentially these massive mathematical functions. And a parameter is essentially a variable in that mathematical function. So the more the parameters you have, the more degrees of freedom you have. So essentially, a parameter is essentially the weight between the connections of a neural network. Loosely, you can connect to it as a brain. It's a synapse between neurons, right? So the more you have of these, the more flexibility you have in predicting the outcome given the input. So in a mathematical terms, when you say 530 billion parameters, that means a high dimensional space of 530 billion dimensions. So you can imagine that when you have a space that big, you can fit a lot of information in this, and you can distinguish different parts within that space very easily.
Thank you. I'm just going to go quickly to online audience question. Bill from Public Relay asks, how do these models do at making inferences about concepts? And he gives an example, beauty is in the eye of the beholder, but who is the beholder? So, I'm guessing, Bill, that you're sort of asking, does the model internalize its own sort of concept of beauty, or is it mirroring other people's concepts?
Yeah, it's difficult to say. I mean, the model is the beholder in this case, I guess. And I talked about the beautiful sunset on the sea. What is the idea of beautiful? It probably picks up from that some concept of what beauty looks like. But I mean, that's a hard thing to say. Right now, I wouldn't say that we can translate feelings or concepts in neural networks very well. We can do modalities, so anything that is visual and is objective, these models can very easily pick. But something that is subjective, like beauty, will be difficult to capture.
Yeah. Anything in the room? Yeah. There's one over here on the side.
Hey, thank you. I used to work for Microsoft, a great company. I have a question about, you mentioned the computing costs and everything. How about energy consumption? I know that Microsoft is trying to put, data centers underwater and on the ice. Things are growing so fast. What about the environmental impact of all that?
That's a great question. This is something that we should be cognizant of. I can give you the overall answer, which is like everything costs energy, right? Every time we shoot a Falcon 9 rocket into the air, it consumes a lot of energy. Every time we take a jet flight somewhere, it takes a lot of energy. These models do consume energy. But from a Microsoft perspective, we have to take things as a whole. The company is committed to be carbon neutral by the year 2030, and we've committed to be carbon negative by 2050. So the way I think about it is we borrow some tokens to advance the state of AI, and the company is committed to making sure that we pay it back so that the entire humanity benefits.
On a related note, I mean, it's not just the sort of environmental costs, but just in terms of the resources you need. I mean, you mentioned the amount of compute you need for it. I mean, this is sort of out of reach of most, but the wealthiest, largest labs. So, I mean, how does Microsoft think about that?
So the way to think about it is, and I talked about this in the talk, is you don't need to be able, you don't need to create a neural network on your own. We need to be able to adopt these large. So only a few houses, research houses, should create these. And then everything else, because these models have these amazing abilities of transfer learning, you can actually solve a lot of these problems just by using these models off the shelf. Mm-hmm. You don't need to train this, because otherwise, it's going to be impossible, and the energy cost will be a big factor also.
Now, we've got a few questions coming in from the audience. More than one person is asking about bias and ethical issues. But just in interest of time, and feel free to say something about that, but we're going to have OpenAI talking about their approach to that in a few minutes. And I think what they will talk about sort of applies to large language models. So the point I'm making is, if Ali doesn't talk about this, it's not because Microsoft is not thinking about it. This is applicable to anyone making these models. Yeah. But I mean, do you want to say something briefly?
Yeah, maybe in 30 seconds. Microsoft is absolutely committed to making sure we are using these models in a responsible way. We have a responsible AI, Office of Responsible AI that oversees every single deployment of AI models in the company. We have Ether principles that talk about responsible AI principles, not just for Microsoft, for industry as a whole. But in general, I feel like building these large models is just one aspect. Putting them into production is where the rubber meets the road. The users are harmed when these models are put in production. So we need to make sure that we are very, very careful when these models are being put in production. So that's why I talked about the test set. We need to make sure that we have comprehensive coverage when we are putting these models in production. And that's where your users are actually interacting with these.
Okay. Well, I'm going to leave it there. Ali is going to be in the reception room, and we're happy to answer questions later.
Thank you so much.
But for now, thank you. Thank you.